Hello there, warriors. It's Miss Lemons, and today we are going to continue our conversation of thermochemical equations by incorporating a little bit of stoichiometry. That means dimensional analysis is back. Before we get started, though, I did want to touch upon just a little review quick, specifically the values of delta H and Q. So remember that if you have an endothermic reaction, energy is absorbed and heat is a reactant. So we would have to incorporate it into our chemical equation as such, or we could write it as a positive value here. And if we have a positive delta H, that also means we have a positive Q and a positive T, delta T. Exothermic reactions, remember, that is when energy is released. It's exiting the system. Heat, therefore, is a product. It's produced. And so we could incorporate it into our thermochemical equation by adding it to the end as a product, or we could write it off to the side like a footnote as a negative value. Remember, if we have a negative Q, we also have a negative delta H, and we have a negative delta T. Okay, so let's go ahead and practice. And before we do that, we need to kind of refresh our memory on the finer points of conversion factors and formulas. So these are the conversion factors that we are going to be using today. Actually, we don't even use the particle ones at all today. It's possible, but it's not going to happen as often as you think. The focus here, remember, we've got 1 mole of X is equal to number of grams of X, and that number is from the periodic table. It's the molar mass, grams per mole, right? 6.02 times 10 to the 23rd particles of X per 1 mole of X. And then we have number of moles of X for number of moles of Y, and that is the mole ratio that comes from the balanced chemical equation, and we use those coefficients in front of each substance. And then we also have this new conversion factor on the bottom, number of moles of X, which that number comes from the balanced chemical equation, and then the number of kilojoules of heat energy in that chemical equation. So let's go ahead and give this a shot. Question 1. When ethanol is burned, it reacts with oxygen. It also releases 1,368 kilojoules of heat energy to the surroundings and produces CO2 gas and H2O gas. Okay, so I need to complete and balance the chemical equation below. Remember to include heat. Well, the nice thing about this, guys, is that my chemical equation is already balanced, and you really will not have to worry about balancing chemical equations because we already assessed you on that in Unit 7. So the focus here is incorporating that heat value. And whenever I'm trying to incorporate the heat value, I always refer back to the word problem and see if there are any key words that maybe tell me whether this is an exothermic or an endothermic reaction. My eye is automatically drawn to releases 1,368 kilojoules of energy. Releases tells me that energy is leaving the system or exiting the system. Therefore, this is exothermic and heat is being produced. So therefore, heat is a product. So we can add it to our chemical equation just by placing it on the end, adding it into the chemical equation. Now, I know some of you might be looking at me and say, but wait, Miss Lemons, isn't that supposed to be a negative value? And the answer is no, not when it's inside the chemical equation. We know that this is going to be a negative value if we calculate with it because it's leaving the system, but when it's incorporated into the chemical equation like this, we can already see that it's leaving the system. If you would like to write it a different way, the way that I like to write it, heat as a footnote, you'll see that here I have incorporated that negative symbol to show that heat would be a product if we were to write it into the chemical equation, and that heat is exiting the system. Now, this is a complex unit, so that means when I read this unit out loud, it's 1,368 kilojoules of energy per 1 mole of substance released. Okay, that's important to remember because it's going to help us with calculations on the next slide. So, letter B, calculate how much heat energy in kilojoules is released when 12.5 moles of ethanol burns. Okay, so I've gone ahead and I provided you guys with your conversion factors. And before I even do anything, I'm going to just read this question again and see what I'm starting with and where I'm going to. So it says that it's asking for heat energy. So my final stopping point is heat energy, and I'm given moles of ethanol. Okay, so I've got my start, I've got my stop. Now I need to whip up a few conversion factors here to get us from point A to point B. So here, I'm going to go ahead and rewrite the chemical equation. I like to write it like this with heat as a footnote because the value of heat is negative, or the sign is negative, and you have to use that in your calculations. So, but you are welcome to write it the other way. So we're going to start with what we know, which is 12.5 moles of ethanol. We have moles of ethanol. And I know that I'm going to be placing that over a unitless 1 so that we line up our numerators and denominators. I know that I need to multiply this by some sort of conversion factor. So on the bottom, I know that I should have, if I have moles of ethanol on top, I need to have moles of ethanol on the bottom. Now, the problem with this is that every single one of these contains moles. So we want to try and pick something that gets us closer to kilojoules. So yes, any one of these would work, but it depends on where you're going when you pick which conversion factor you're going to use. Okay, if I have moles of X, do I want to get to grams of X? Moles of ethanol to grams of ethanol. And the answer is no. We want to get to kilojoules. Okay, if I have moles of ethanol, do I want to get to moles of CO2? No, I'm trying to get to kilojoules. Well, if I have moles of ethanol, do I want to get to kilojoules? The answer is yes. So we're going to be using this conversion factor here in the bottom right. Okay, so I'm going to put moles of X on the bottom, moles of ethanol on the bottom, and you'll probably wonder, okay, Miss Lemons, where did you get that 1 from? Well, the 1 actually comes directly from the balanced chemical equation. The amount of heat energy is going to be the heat content of that system. Okay, so I put that into our conversion factor with the negative sign. The sign is so important. Okay, so I'm going to go ahead and multiply my numerators together to get a new numerator, multiply my denominators together to get a new denominator, and I know that I've set this up correctly because you can see that I have moles of ethanol on top, and it's being canceled by moles of ethanol on the bottom, which would leave me with just kilojoules, hence why there's no unit down here. 17,100 divided by 1, and notice that I have a negative in front of there. I'm still using that negative. It's still a part of my equation. It's still part of my calculations. And then we're going to divide the top and bottom, and that gives us 17,100 kilojoules. And that's not of any sort of, it's not of ethanol. That's just kilojoules of heat that were released. But you don't even have to say released because you have that negative sign there. Okay, so let's take a look at 1C. Calculate how many moles of carbon dioxide are produced if 787 kilojoules of heat energy are produced. Okay, so again, I like to go through, kind of see where I'm starting, where I'm going. It's asking me for moles of carbon dioxide, and it's giving me heat. So I'm going to go ahead and rewrite my thermochemical equation with my heat content and its beautiful little symbol there. I need that negative. And I'm going to start with what I know. I know that only 787 kilojoules of heat energy are produced. Now look what I just did there. I wrote down the number, but I put a negative sign in it. And you're like, oh, darn it, I didn't know that. I totally forgot about the negative sign. Well, that's why word problems are really important. If you're doing calculations with heat energy, signs matter. Even though it doesn't say negative 787, you know that this is going to be negative because heat energy is produced, it's released, it's exiting the system, and therefore it is a negative heat value. So we need to make sure that we're putting our negative sign there. So I'm starting with negative 787 kilojoules of heat energy, and I'm going to put that over a unitless 1. Then I know I'm going to be multiplying this by a conversion factor. So if I'm starting with heat energy, the only one that I can actually use of the 4 conversion factors is the bottom right-hand one because it's the only one that contains kilojoules of heat. So I know that I'm going to put, if I have kilojoules on top, that means I'm going to have kilojoules of heat energy on the bottom. So I'm going to use the heat content that I have from my balanced thermochemical equation, and notice that it's also negative. And then if I use 1/2 of my conversion factor, I have to use the other half of my conversion factor. So moles of what? Moles of H2O, CO2, O2, ethanol. It's asking us for moles of carbon dioxide. So I want the other half of this conversion factor to be moles of carbon dioxide. And I'm going to use the number from the balanced thermochemical equation. So that's saying for every 2 moles of carbon dioxide produced, 1,368 kilojoules of energy are released. Okay, so now I know that I've set this up correctly because kilojoules on top cancels with kilojoules on the bottom, and then if I don't do anything else, I'm going to be left with moles of carbon dioxide, which is what this question is asking me for. So multiply your numerators together, multiply your denominators together, go ahead and divide the top and bottom, and you should end up with 1.150584. We only need 3 sig figs, so that's rounded to 1.15 moles of CO2.